Well, welcome to the Notes for BC Calculus 1.7. As you can tell from the background music, I am making this video right before Christmas. And this is the last video before I come back from Hawaii. So hopefully you guys are doing well as I am gone and looking forward to seeing you guys again soon. Okay, oops. Did not mean to do that. All right, what we're talking about today for 1.7 is improper integrals. This is a BC only topic. In fact, the rest of the year, everything that we're doing is BC only. So it was only those first few lessons that were AB topics. They just were topics we needed so that we could get to things like this. All right, so just like fractions can be improper, so can integrals. And so here's what it means if an integral is improper. There's a couple different ways that this could happen. Any of these would be the way that we would describe something improper. The first one, if the integrand becomes infinite at one or more points in the interval of integration. So imagine that somewhere inside the integral's limits, you have something like a vertical asymptote. Okay, that can happen. There's a point of discontinuity at an endpoint or in the interval. And to be honest, the second one kind of covers the first one as well. And then this is the second most common way to see it. One or both of the limits of the integration is infinity. Typo. Woo, infinity. There we go. Or negative infinity. So positive or negative infinity. Maybe I was trying to use a noun there. Infinite. There we go. That works. So here's the actual process, and we'll kind of come back to this when we have some concrete examples because it'll make a little bit more sense. What you're going to do is you're going to replace the endpoint of the integral that's causing a problem with a constant. A is commonly used, as is B. You can actually pick any letter that you want. I would avoid C because we tend to use that for the constant at the end of an indefinite integral, so you kind of want to avoid something that's already commonly used. You're going to go ahead and integrate the expression and evaluate. And we are going to take the limit. We're going to be taking a limit. And the limit notation is going to be really important. Your limit is going to be as A approaches whatever problematic value exists, either point of discontinuity or infinity or negative infinity. If that limit exists, remember, limits exist when they equal a concrete number. So they have to equal some number. It can't equal positive or negative infinity. Then we would say that integral converges to a specific value. Whatever the value of that limit is our answer. If the limit does not exist, you get something like positive or negative infinity, or you get something undefined. We are going to say that integral diverges. Now, those phrases converging and diverging are ones that we're going to actually take a closer look at when we hit chapters 3 and 4. So we'll kind of come back to those definitions at a different time. For now, we're just going to use them as vocabulary in this context of whether or not the limit exists. All right, let's take a look at the first one. If you notice this definite integral, instead of having two numerical values for our upper and lower limits of the integral, our upper limit is infinity. This is an example of an improper integral. So what we're going to do is we are going to, and by the way, this also has a discontinuity. This is discontinuous at 0. However, 0 is not my interval, so I'm actually not worried about that. It can be discontinuous outside of my interval and give me 0 problems. But what does give me a problem is the fact that I have this infinity. Now, the notation for improper integrals, I will be very, very picky on, and a lot of students don't believe me on that, and then they get really sad when they get their quiz on this or when they have a test on this and they get their score back because they don't understand why, if a problem is worth like 8 points, why they missed 5. And it might be because they're poor notation. So please watch carefully. We're going to start off by writing a limit. This is going to be the limit. I'm going to pick a variable. I tend to use A. As A approaches infinity of the definite integral from 3 to A of 1 over x squared dx. I'm going to write that as x to the power of negative 2 dx because I'm anticipating that when I integrate this, I'm going to use the power rule. That limit notation must be there. And so to write the limit, whatever variable you want to pick, I picked A, you're going to say as A approaches that previous limit of infinity. Now, I need to continue writing the limit notation in here until I substitute in. So I'm going to go ahead and keep that notation here, and I'm going to do my definite integral, add 1 to the power, divide by that new power. This is going to be evaluated oops, there we go. Almost lost my negative. Evaluated at a and 3. You might wonder, how do you evaluate at a? You just replace x with a. So my constant multiplier of -1 I'll pull out, and this would be 1 over a minus 1 over 3 when I evaluate this. And now I'm going to actually replace a with infinity. So if I have 1 over a very, very large number, think about your horizontal asymptotes. 1 over something increasingly larger would approach 0, minus 1/3, which becomes 1/3. And this converges to 1/3. Our actual answer is 1/3. So whatever the limit is what the actual answer is for the definite integral. Now, this whole converging that I'm writing is not part of your answer. I'm just trying to connect to the vocabulary up here. You don't actually have to write that if you don't want to. So I encourage you on this next one to pause the video and try this one yourself. And when you're ready, go ahead and restart the video. It's very similar to the last one. This one also has a discontinuity. This discontinuity is at -1/3, which is not in my interval. So I'm going to go ahead and proceed by noticing that this is what causes a problem, is this lower limit of -infinity. So I'm going to write this as, I'm going to replace that with a. And I want the limit as a approaches -infinity of -1 over a. And then this would be 3x plus 1 to the power of -2 dx. Now, a lot of students go, I don't need to write the limit. I can still do this with the -infinity and just see what happens. That's true. You can get the answer, but you will not get the process points in between without writing the limit, because what we're actually doing is replacing it with a limit. We are saying what would happen if we have a constant there that's close to it. So your math would give you the right answer, but because your process would be incomplete, you would not be getting full points, so you have been warned. All right, now notice that this is basically, the form here is u to the power of -2 for this integral. We do have chain rule. If you want, you can be very, very formal with the chain rule here and let u equal 3x plus 1, and du would be 3x dx. And notice we would have to use a 1/3 divisor. Wow, how about 3 dx? 1/3 divisor to get dx alone. You can do that, but I think we've been working on recognizing what the chain rule does, and if that chain rule would have just been a constant multiplier, we just want to divide by that value. So this would be 3x plus 1, add 1 to the power, divide by that power, and then I want to divide by the 1/3 to undo the work that the chain rule would have done. And this is going to be evaluated at -1 and a. I'm going to keep my limit notation until after I've written a in the definite integral. So I'm going to factor out, or in the evaluation, I'm going to factor out the -1/3, and I have left 1 over, because that's what the power of -1 is. When I replace this with the -1, I'd have -2 on that denominator, and then minus 1 over 3a plus 1. And I'm going to replace my denominator with -infinity. Now, at this point, I'm replacing this with -infinity. By the way, if you wanted, you could actually write it. It's kind of up to you. Okay, this step right here is optional. If it helps you process better, go for it. But I would have -1/3 times -1/2 minus 0, 1 divided by an increasingly large value in the negative direction. And so my final answer here is +1/6. This next type's a little bit different. Take a look at our limits. At first glance, many students wouldn't recognize this as an improper integral because I don't have that positive or negative infinity. However, what I do have is I have a discontinuity at x equals 2. And at x equals 2 is in the limit of my integral. So this right here, be careful on your notation here. This first line is really important that you write this line in its entirety. What I'm going to do is I'm going to recognize that I need to split this at 2. All right, so I would have like -1, and I would want this to stop at some value here. And then I would want this to pick up at a value here as well. These are both going to need limits. This limit right here would be as x approaches 2 from the left. Since right here on this one, we're going to approach 2 from the left side because I'm going from -1 up to 2, and then I'm splitting it right at 2. I'm kind of jumping over what's happening at the 2, if you will. And then I'll write this as x minus, or 1 over x minus 2 dx. You might recognize this form as natural log. This one's also a limit. Oh, this is not x. Lost my mind. This is as a. Now, I chose to use a different variable here as b approaches 2 from the right on this one. Because I'm approaching different values, that just made sense to me to switch the variable. Sometimes I've seen some people write a and a. I think that's a little bit less common, but I don't think anyone's going to freak out if you do that. Over that same expression, dx. Now, from this point, you can pick one side or the other to work with. It's really kind of up to you. But I'm just going to pick one of the sides, and I'm going to go ahead and I'm going to do my definite integral like I would have before. And then if I get a numerical answer, I'll also do the left side. If, however, I get something either undefined or positive or negative infinity, I will stop, because if one side diverges, then we don't need to check the other side, because if we combine that with a constant, like infinity plus a constant, that whole thing would diverge. I'm still going to keep my limit notation. The limit as a approaches 2 from the left. And now this is the form of natural log. This would be natural log of the absolute value of x minus 2 evaluated at a and negative 1. And notice that this particular one, the chain rule didn't do anything, right? The chain rule of this argument would have been multiplying by 1, so there's nothing that we have to do there to undo that. So at this point, I'm going to go ahead and rewrite this. This is the limit as a approaches 2 from the left of the natural log of the absolute value of a minus 2 minus the natural log of the absolute value of negative 1 minus 2. Well, this would be if a is a 2, okay, we're approaching it from the left side, but if a is a 2, I would get the natural log of 0 minus the natural log of negative 3, absolute value of that is positive 3. The natural log of 0 is undefined. So since we have this undefined portion of this, it doesn't matter if the rest of it is defined. If part of it is undefined, we stop and we say it diverges. So I didn't actually ever evaluate that separate second integral. However, this whole first piece is really important. And usually on the AP exam, if you don't have that whole first piece, they will stop reading the problem. So you want to make sure you get that first portion there correct. All right, this next one also is one with a discontinuity. This discontinuity, however, is at an endpoint. So I don't need to split this, but I still need to notice that there's a discontinuity at 0. So although this doesn't have infinity, it still has a discontinuity in my integral. So I'm going to take the limit as a approaches 0 of the definite integral from a to 1 of x to the power of negative 1/2 dx. My goal is to use the power rule here, which is why I'm writing it this way. One other thing I should mention here, since this is an endpoint, we're approaching 0 from the right-hand side of 0. And sometimes kids are like, I get confused. How do I know right or left? Well, look at the direction of where you're going. You're starting at 0 and moving to 1. So we're approaching it from the right side. We don't do that with positive and negative infinity, but if improper integrals, if it's a constant, we do use that direction there, whether it's split in the middle or it's an endpoint. So you just kind of want to think like, oh, I'm starting at 0, moving to the right, which is why I'm going to use a plus sign there for that limit. So then this would be the limit as a approaches 0 from the right of x to the power of 1/2 if I add 1 times 2 when I multiply by that reciprocal evaluated at 1 in a. Sometimes kids don't write that evaluation, and you will not receive all of your process points if you don't. This is the limit as a approaches 0 from the right of that constant multiplier of 2 times the square root of x minus the square root of a. No, wrong. Square root of 1 minus the square root of a. And then a, remember, is 0. So this would be 2 times 1 minus 0, which is 2. This converges to 2. Last one. This one has a discontinuity at x is equal to 5, which is inside my interval. So I'm going to split this. I encourage you to pause the video, try this one on yourself, and then restart it once you're ready. All right, so I'm going to rewrite this, being careful with my limit notation. I'm going to start with the limit as a approaches 5 from the left. I'm going to start at 3 and go to 5. Hopefully you can visualize we're coming towards 5 from the left-hand side for this first part. So this would be from 3 to a of 5 minus x to the power of negative 3 dx. I'm going to be using power rule here. Plus the limit as x approaches, oops, I did this wrong, 5 from the left. I think I said left and wrote right. I apologize, hopefully. All right, as we approach 5 from the right, you cannot read that. I'm doing awesome today. And I'm going to not write x. I'll switch my variable to b. X is my input, not my limit, and so I'm having trouble with that today. You might have trouble with that sometimes too. 5 minus x to the power of negative 3 dx. I'm just going to evaluate the left-hand side. If the this first integral here on the left, if this converges to a concrete number, then I will also add the one on the right and evaluate that, and then I'll add them together. However, if it diverges, then I will stop the process. All right, and by the way, it is possible for it to converge on both, so don't assume one thing or another. You'll see more of that on your homework, but on this particular one, the limit as a approaches 5 from the left, be careful here. This is, when I integrate this, I'll add 1 to the power. I will divide by that power or multiply by its reciprocal, and be careful, be careful, be careful. The chain rule here would be multiplying by negative 1. I need to undo that, so I'll divide by negative 1. This will be evaluated at a and 3. So this would be the limit as a approaches 5 from the left of positive 1/2. Factored out of 1 over, let's see if I plug in a, 5 minus a quantity squared, minus 1 over, let's see, 5 minus 3 is 2 squared, or 4. If I plug in a 5 right here, I get a discontinuity at the denominator. So it's undefined right here. What's happening here is there's a vertical asymptote that's happening at this point. There's that 0 on that denominator that's not repeated on the numerator. And so because I have an undefined value as part of this, this diverges. And I do not need to continue the second part. Do not make the assumption that if there's a discontinuity in the interior of your interval for your definite integral, that this always diverges. I know we did 2 like that. Make sure you do the assignment because you'll have an opportunity to see that this is not always true. It can converge. All right, that is the end of the notes. Hope you have a great day.